Hello, everyone, and thank you for attending today's webinar, P4 Runtime, Putting the Control Plane in Charge of the Forwarding Plane, sponsored by Barefoot Networks, Google, and the Open Networking Foundation. Before we begin, I wanted to cover a few housekeeping items. On the right-hand side of your screen is the Q&A. If you have any questions during the webcast, you can type your question into the Q&A box and submit your questions to our speakers. All questions will be saved, so if we don't get to answer you, we may follow up via email. At the bottom of your audience console are multiple application widgets you can use. If you have any technical difficulties, please click on the yellow Help widget. Here you can find answers to common questions. A copy of today's slide deck is available for download in the green Resource List widget. Towards the end of today's presentation, we'll ask for your feedback. A survey will pop open on your screen and will only take 1 minute to complete. Your feedback is extremely helpful. An on-demand version of the webcast will be available about 1 day of the event and can be accessed using the same audience link that was sent to you earlier today. I would now like to turn the event over to Heavy Readings Analyst at Large, Simon Stanley. Simon?
Thank you. As was said, I'm Simon Stanley, Analyst at Large at Heavy Reading, and I'll be your moderator today. And I'm very pleased to welcome our speakers. First of all, we have Nick McEwen, who is Chief Scientist and co-founder of Barefoot Networks. Nick, perhaps you could just tell us a little bit about yourself and Barefoot Networks.
Yeah, Barefoot is a company building programmable forwarding planes, and I'll be touching on that briefly this morning. And with my other hat on, I'm Professor of Computer Science and Electrical Engineering at Stanford University.
Thanks very much, Nick. Next, we have Jim Wanderer, who is Director of Engineering at Google. Jim, perhaps you could just introduce yourself.
Hi, yes, thanks. My name's Jim, and I work in Google's Platforms group. We do the data center infrastructure, storage, compute, networking for Google's data centers.
And then finally, we have Timon Sloan, who is VP Marketing and Ecosystem at the Open Networking Foundation, ONF. Timon.
Thank you, Simon. Hi, everyone. So the ONF is an operator-led consortium driving change and transformation across the networking industry.
Okay, great. Right. Well, let's get on with the webinar. And we're going to start today's presentation with a short introduction before I hand over to Nick McEwen from Barefoot Network, who is going to go into more details on P4 Runtime. After Nick, Jim from Google will take a look at an important P4 Runtime use case. And then we'll finish with Timon Sloan from the ONF, who will explain P4 Runtime integration with ONOS. During the webinar, there'll be 2 polling questions and a Q&A session at the end. And I do encourage you to take part in the polls and also send in any questions that you have for our speakers as we go through. Well, we're going through a period of unprecedented change in the communications industry with network virtualization and open solutions, replacing fixed function systems and full standardization. Network virtualization based on SDN and NFV has enabled a new ecosystem of virtual network functions running on standard server hardware. These VNFs can run on servers within large data centers or on appliance platforms located at the edge of the network or on the customer premise. In many networks, the servers are connected through white box switches where the control plane and operating system can be configured by the operator, delivering a very flexible networking solution. Network virtualization has been developed relatively quickly through the use of open solutions, building on the open approach developed by the Linux community. These open solutions include OpenFlow, OpenStack, OPNFV, Open vSwitch, and ONOS. ONOS is an open-source SDN network operating system for carrier-grade solutions, and we'll be hearing more about ONOS from Timon later. There have also been some key technology developments in switching and packet processing. Switch chipset architectures are evolving quickly. Switch chipsets were initially developed with fixed functions and multiple chips to deliver the highest performance. This functionality is now usually integrated into a single device, taking advantage of the latest silicon technology. And as networking has developed, vendors have added multiple configuration options to those switch devices, and there are now several devices available that support programmable packet processing. This allows the switch developer and the network operator to optimize the packet switching and forwarding for a particular application. The P4 packet processing language was developed by a group including Intel, Microsoft, Google, Barefoot Networks, Princeton University, and Stanford University. P4 is used to specify packet forwarding behavior and is already seeing significant interest in the industry for both switching and smart NICs. P4 is being further developed through the open source consortium p4.org, and we will hear more about this during the webinar. P4 allows developers, including operators, to develop hardware-agnostic switching and forwarding solutions that can then be deployed on hardware platforms from different vendors as required. P4 can also be used to support a move from OpenFlow to a more flexible solution based on P4 Runtime. On the left, we have an OpenFlow solution using an OpenFlow controller and OpenFlow agent. The OpenFlow agent communicates with the switch hardware through an extraction layer and software stack, or SDK. On the right, we have a P4 Runtime-based solution using a P4-aware controller and P4 Runtime agent. This approach is significantly more flexible and requires less software intervention in the forwarding plane of the switch. And we'll be hearing more about all of this as we go through this webinar. So this brings us to our first audience poll, and the question we'd like to ask you is, how familiar were you with P4 prior to learning about this webinar? Is it something that you've contributed to? Are you very familiar with P4, slightly familiar or aware of P4, or not familiar at all? So if you'd like to put down your votes on which of those are most appropriate to you, and we'll go on to the answers in just a moment, and we've got the results coming in. Please keep putting in your votes there. Just to let you know that the webinar will be archived after the event, usually within about 48 hours. So if you want to come back, or if anyone was unable to listen today, that archive will be available. Right, so we've got a good number of responses come in now. If we go to the results, it should be coming up on your screen now. Okay, so I think we've got a pretty good response there. So almost 50% slightly familiar, and another 30-odd%. So we're looking at well over 80% know something about P4. Nick, does that sort of reflect what you're seeing with P4 now in the industry?
Certainly P4 is gaining sort of interest, in part because of the ability to program the forwarding plane, but also just to specify existing behaviors and specify behaviors that perhaps we've used for a long time in an unambiguous way. So yeah, it seems to be gaining quite a lot of interest. Okay, great.
Right, with that, I'm actually going to hand over to Nick, who's going to tell us more about P4 Runtime.
Thanks a lot, Simon. Yeah, I'm going to be telling you about the P4 Runtime project, it's an open source project that we originally started between Barefoot and Google, and more recently has been joined by ONF-A. And it has the goal of putting the network control plane much more firmly in charge of the forwarding plane. So the basic idea is to make sure the APIs we use to control switching ASICs are open and very easily extended over time, even if the forwarding plane behavior is completely changed and upgraded. So here's a cartoon picture of the insides of a switch or a router. It runs a switch OS, typically based on Linux, which talks to a switch ASIC below. So the protocols and features that we typically use are implemented as user-level processes, and they communicate with their peer processes on neighboring switches to build up the forwarding tables in the switch. And they also communicate with the switch ASIC via an API to control it. So today, this is pretty much how all network switches and routers are built, whether they're from networking equipment vendors or they're homegrown by big web-scale companies. In the past, the API was closed. It was fixed and proprietary and only available under an NDA. It was fixed because the functionality of the switch ASIC was also fixed, and the protocols and features it supports were baked into the hardware. The conventional wisdom at the time was that it's just too hard and too expensive to make the switch chip programmable, and so we should simply only implement the set of protocols commonly found in many networks and then implement them in a fixed function device. This in turn justified a fixed API as well, with little or no need to extend the API over time. And then to discourage customers from using other switching chips, the NDAs and license agreements prohibited sharing the APIs with others. When such artificial barriers are placed on competition, it usually leads to designs that are poorly structured. They tend to become unwieldy and complicated over time. It stifles competition in the marketplace, and it just ossifies the way that we build networks. So one attempt to open up the interface was OpenFlow, shown here. OpenFlow was designed to let a remote control plane control a set of switches like the three shown here. Back in 2007, when OpenFlow was first conceived, we wanted a common way for software control planes to remotely control switches from different vendors. We noticed that in most networks, the switches do pretty much the same things, Ethernet, IPv4, etc. And if we could find a standard open interface to populate the forwarding tables in these different switches, such as the hash tables for Ethernet address lookup, the longest prefix match tables for IPv4, and so on, then a single control plane could control switches from a variety of different vendors. The main goal was to make it easier for those who own and operate networks to write better control planes, and we can see that it worked, as many big data centers today are built using homegrown control planes that leveraged open interfaces to the data plane. But while OpenFlow is an open standard and can be used to control different types of switch, it's important to remember that OpenFlow assumes the switches have a fixed, well-known behavior described in the datasheet of a switch ASIC. It takes about 4 years or more to add a new protocol to a fixed function ASIC, and so OpenFlow could get away with being relatively fixed as well. But OpenFlow grew over time from supporting 4 common protocols to supporting over 45 today, and anyone who looked at it would agree it wasn't designed to be extended, and as a result it's become really quite unwieldy. One shortcoming of OpenFlow is that it only mandates the fields in a packet that we should match upon. It doesn't define the actions you should perform after the match, for example, decrementing a field or encapsulating a header. And unfortunately, different switch ASICs implement the actions in different ways. OpenFlow therefore suffers from being fixed and ambiguous in its behavior. SAI, or SAI, the switch abstraction interface, was designed to solve a similar problem to OpenFlow, but for networks in which the control plane is inside the switch. And like OpenFlow, SAI can and is used to control switches based on a variety of different switch ASICs. But also like OpenFlow, SAI is a relatively fixed API that is getting more complex over time. And so this led a group of us to wonder what kind of API you would want if the underlying switch ASIC is itself programmable rather than fixed. In other words, the behavior of the switch ASIC is defined in software from above rather than by a datasheet from below. If the control plane can download a program to tell the switch how to process packets, then the switch can use any API it chooses. And this led us to consider the following challenge. Can we design an open, silicon-independent API that is easily enhanced and extended as we evolve the forwarding plane, and one that can be used equally for local or remote control planes? If we could define such an API, then network owners could get the benefit of a silicon-independent API without having to adopt the lowest common denominator of existing fixed switching silicon. And fortunately, at this time, 2 recent technologies have proved to be a big help. The first is the new language P4, which lets us describe the way in which we want to switch to process packets. In other words, instead of the switch telling us, we now have a way to unambiguously describe and declare how we want packets to be processed. The second is the emergence of new P4 programmable switching chips. These are switch chips that we tell what to do rather than them telling us. We write a program in P4 describing how packets should be processed and what protocols should be supported. Then we compile it and download it to the switch chip. Barefoot has built such a chip called Tofino, but we can expect more P4 programmable chips to emerge in the next few years. The P4 language was originally written by a group of people from Barefoot, Google, Intel, Microsoft, Princeton, and Stanford. And since then, it's grown into a much bigger Apache-licensed open source project with membership from across the networking industry. And I'd strongly encourage you to visit p4.org to learn more about it. Today, there are active working groups developing the language, building open source compilers and tools, and contributing new P4 program. Let's take a look at an example of a P4 program. In the example I'm going to show, I'm going to use the generic PISA, or Protocol Independent Switch architecture, in which a pipeline of identical match action stages are going to process packets. Notice all the stages are the same. Arriving packets are parsed according to a program described by the user. And then the packet header fields are going to be processed by the match action stages. In each stage, one or more fields are matched in the memories, and then actions are performed on the headers, such as modifying a field or adding a new header. This generic PISA architecture is a good starting point for understanding how P4 works. Here I show a simple P4 program consisting of 3 parts. In the middle in gray is the description of packet headers that will be recognized by the program. In this example, it defines what an Ethernet and VLAN header look like in familiar C-like syntax. The parser program on the left in green describes how the packets are parsed to find and extract the headers that we need to process. Finally, the program snippet on the right in blue describes what kind of lookup tables we need. For example, exact matches for an Ethernet header and a longest prefix match for an IPv4 address. And it explains the control flow for a packet passing through the pipeline. P4 programs like this can be compiled to run on a number of different devices, including Xilinx FPGAs, Metronome SmartNICs, can be even used to define how OpenVSwitch processes packets in the kernel. P4 is carefully designed so that programs can run on very fast programmable switch chips too, and I'll describe one next. The Barefoot Tofino switch is programmed using P4 and is currently the world's fastest switch chip. It has 65 ports of 100 gigabit Ethernet and processes several billion packets per second. One interesting property is that P4 programs always run on Tofino at line rate. I expect that soon, frankly, all switches will be built this way. They cost the same, they have the same power, and they run just as fast as 6-function switch chips. And of course, they can easily be reprogrammed as needed. So the user starts by writing a P4 program. For example, a top-of-rack switch described here in tour.p4. It might include protocols like Ethernet, IPv4, ECMP, and so on, and it would likely include INT, or in-band network telemetry, which gives unprecedented visibility into what packets are doing. The P4 compiler generates the configuration for the switch, and that's the orange line shown at the bottom. But it can also generate the API as well. Because the switch can be programmed however you want, it has no predefined API. We can use whatever API makes most sense for the task at hand. So now let's return to the challenge we set ourselves. Can we design an open silicon-independent API that is easily enhanced as we evolve the forwarding plane, one that can be used equally for local or remote control planes? Imagine we're updating our tour.p4 program to add an IPv6 table. So first, the compiler generates the new program and configures the switch. Next, the compiler tells the P4 Runtime API about the new IPv6 table. Because the API between the control plane and the switch is derived directly from the P4 program, when we add a new table to the program, we can automatically generate the API to talk to the table. And then we can add it to the P4 Runtime API. The control plane can immediately start using the new table API without needing to restart the API or the control plane. This can lead to much faster design and evolution of the forwarding plane because we can add new features to it without spinning the chip or even rebooting the control plane. And so, in summary, the P4 Runtime API is open, silicon independent, and easily extended as we improve the behavior of the switch chip. And of particular importance in big networks, the control plane can add new functionality to the switches without needing to reboot the API or the control plane. Let's take a slightly closer look at what's going on. On the left-hand side is a snippet of our tor.p4 program, including where a table is defined. On the right is the usual commands a control plane might use to update the table during runtime to add new rules. The compiler generates the logical view, which in turn creates an encoding used directly by the protobuf in the RPC channel between the control plane and the switch. The P4 Runtime API has been automatically extended by just adding the new schema to the existing API. The control plane can start using it immediately. Notice that this can work just as well if the control plane is on the same box as the switch ASIC. In fact, it would work in exactly the same way. The API is silicon independent, easily extended, and the forwarding behavior can easily be upgraded without needing to reboot the control plane. And so in summary, existing APIs are either hidden behind NDAs or they're hard to extend. Changing an existing API typically requires a lot of work and a major interruption of service. The P4 Runtime API is easy to extend by its very design. The API is derived from the program that describes the forwarding behavior. The P4 Runtime API can be used equally well by a remote or a local control plane, and the control plane does not need to be interrupted when the API is changed. And so with that, I'm going to hand over to Jim Wanderer, Engineering Director for Networking at Google, who's going to talk about a particularly interesting use case for P4 Runtime.
Thanks, Nick. This is Jim Wanderer, Google's platform group, and I'm here to talk about what we see as the future of SDN switching. Over a decade ago, we realized that our data centers needed much larger and much higher capacity networks than could be achieved with traditional methods. So we used simple switches as building blocks to create multi-stage CLO networks. This gave us inexpensive and high capacity, high performance networks, and this approach worked very well for multiple generations, delivering exponential growth in our capacity. However, with this approach, at the time, we needed to build our own custom hardware. For more information on Google's history of our networking in our data centers, please see our SIGCOMM paper, Jupiter Rising. Around 2010, OpenFlow arrived, and we started adopting an SDN architecture for our systems. This allowed us to centralize the control of our network with the brains of the network running on standard compute servers. This allowed us to make large-scale, flexible networks with sophisticated features addressing special needs around security and integration with our Google production systems. This whole approach was key in building our very large 1.3 petabit Jupiter DC data center network. So OpenFlow changed the way we built networks, but there were limitations. We no longer had a fully proprietary solution, which was a good thing, but the OpenFlow's limited interfaces required us to do some special things. We needed to scale, we needed special features. As Nick mentioned, the interfaces into OpenFlow could be a bit ambiguous. While the matches were well defined, we couldn't always precisely describe what the actual impact would be for a programming action on the behavior of the network. This led to inconsistent behavior with different types of switches that we used to build our networks. To address this, we had to add special workarounds and extensions to the protocol, and we had to write detailed specifications for what the behavior was for certain types of programming into our network. This resulted in a customized version of OpenFlow, and we weren't able to take third-party devices supporting OpenFlow and drop it into our network fabric. And while previously we did need to build our own hardware, that's no longer true. There are excellent choices available for building these large-scale data center networks. The white box and bare metal switches from various manufacturers and providers are great building blocks for large-scale networks. We'd like to use these devices because off-the-shelf hardware lets us leverage new technology quickly, gives us high velocity, fast for us to deploy, but it's very difficult for us to integrate these into our networking solutions. And the reason is the software. It's a large software effort it's time-consuming and expensive to incorporate these new systems. This comes from a couple of different things. One of them is the platform-specific software. The drivers in each of these platforms work slightly differently. ASIC SDKs are generally proprietary and work differently. And to make these work in our networks, we would need to port the Google OpenFlow extensions and workarounds to these new platforms and make OpenFlow programming work the same way on different chips. This is a daunting, time-consuming, expensive effort and almost makes standard routing protocols sound better. They're interoperable and they are not tied to a particular hardware platform. However, SDN has been a critical enabler for our large-scale, high-performance networks. We need SDN. So we need to get it to work for us and achieve our goals. With our goals being making it fast and easy to use the best and newest hardware and give us high velocity in introducing new features into our network. So, and what would do if we can make an SDN switch that was easy for us to program and control, easy to configure and manage, and provided a silicon and system abstraction to make it independent, then that would be a system we can use to build our networks. How? What is the best way to do this? We believe we can make such a switch by using P4 Runtime to control it. We would program the switch forwarding pipelines with a P4-based control. We would manage and configure the switch using OpenConfig and the network management and network operations interfaces that OpenConfig defines, and we would achieve platform independence with the Open Network Linux Platform, or ONLP. This gives you a powerful multi-vendor solution for building SDN networks. Okay, a little more detail. First about P4, as Nick described, P4 was designed for programmable pipelines. We found it very useful to apply to fixed switches. So we use P4 to detail and specify the functions that we use in our application. We can use P4 to document the requirements and assumptions we're making when we build our system and build these networks, and we don't have to write separate documentation. This makes the chip behavior explicit and well-defined, and we can describe the specific tables and functions that we use using P4. On the left, you see a simple abstract pipeline that our applications might program, and on the right, you can see a snippet of P4 that defines some of the functionality that is important to our applications. Then, based on P4 Runtime is a protocol that allows us to configure the forwarding plane. We push the forwarding state to the chip, and the P4 definition allows us to explicitly define the API and the results we get from programming the forwarding plane. We don't need to use the extra specs for the behavior. This protocol allows a controller to act on specific tables with read, modify, insert, and deleting entries in the switch tables. This gives us a contract for the programming interface that becomes it's OpenFlow-like but well-defined. The way we're using P4 Runtime is with a centralized controller that's been enhanced to support this protocol, and we replace the OpenFlow agent on the switch stack with the P4 Runtime agent. This runtime agent serves as an interface to the switch ASIC and provides access to the switch tables. We're using gRPC as a transport between the controller and the switch. Other transports, such as Swift, would work fine also. We're using remote control. We use centralized remote control, but local processes and routing protocols running on the switch would also use this interface in the same way. Note that we're making no assumptions about the ASIC. The ASIC can be fixed, it can be programmable, or it could be some hybrid. Okay, but how do we handle the variation between chips? How do we address the complexity of putting different types of switches in our network? Our approach is to use P4 to define an abstract logical pipeline. So this is an abstraction, this is an interface that a controller would see, and the controller would program to the logical pipeline. Then this logical pipeline is mapped onto a specific physical implementation. Because P4 is a compiled language and has a compiler, we can leverage that compiler for smart mapping of a logical pipeline onto a physical pipeline. This allows us to put different types of ASICs into our network, and a controller just sees a common logical interface and interacts with all different types of switches in the same way. So the different implementations of ASICs are abstracted into a single model. And the P4 compiler and the software running on the switch are responsible for mapping that logical pipeline onto the actual physical implementation. In this way, we can drop new devices into the network with no changes to our controller. In addition to programming the network, managing and configuring multi-vendor networks is still a challenge. We think the right approach is to use OpenConfig. OpenConfig can fill this role. OpenConfig brings a declarative configuration and provides streaming telemetry where data is streamed off the device to collectors. It uses a model-driven management scheme for operations, and it has a network management interface and a network operations interface to configure, manage, and operate the device. It's based on vendor-neutral data models, and it's being defined by a group of operators who run large-scale networks, and these operators have real-world problems to solve, and so the design of OpenConfig is addressing these practical needs. To address differences at the platform layer between systems, where systems have different drivers and different logic handling hardware at the system level, for things such as pluggable media, fans, temperature sensors, which are all handled differently, we're looking for ONLP, the Open Network Linux Platform, to be the abstraction layer to allow us to inventory, manage, and monitor all these hardware devices. ONLP gives us a consistent API to this platform layer that allows us to run different software on multiple different platforms in the same way. So our end goal is to use off-the-shelf hardware for high velocity and low cost. If we can get the system hardware vendors to provide us system software with ONLP and OpenConfig support, and the chip vendors to provide P4 runtime support for the ASIC and P4 compiler support for mapping logical pipelines to their ASIC implementation, then P4 runtime plus OpenConfig becomes the abstraction layer for switches. This will allow us to easily integrate the best and newest hardware into our networks very quickly with little effort, and allow us to deliver the best solutions to our demanding customers. Now I'll hand it over to Timon.
Great, thanks, Jim. So, hi everyone, this is Timon from the ONF, and in this third segment now, I want to maybe try to package this all together, if you will. We're packaging it into a demo that we're going to be showing live next week, and we want to walk through some of those details. But to start, I think it might be helpful to set the broader context a bit, so to help everybody understand how all the pieces fit together. And so firstly, it's important to understand that the ONF is an operator-led consortium that is backed by the leading operators across the globe, plus a deep membership base of over 150 additional members, including all the vendors you know. And the ONF has had really notable success over the last few years with some very significant projects. I mean, each one of these was, could be considered a home run, I would say. It all started with SDN, or defining software-defined networking, and really taking that from obscurity to the point now where it's broadly accepted as the way next-generation networks are going to be built. That all came out of the ONF, and then OpenFlow, the first protocol to enable separation of the controller from the data plane, and then ONOS, which is now the leading open-source SDN controller for operators. And all three of these built on each other. ONOS uses OpenFlow, and of course OpenFlow is a way to implement a software-defined network. And I want to talk just briefly about a fourth project as well. We do a lot of different things, but CORD is a project that's been getting a lot of attention recently. And CORD builds upon ONOS, which in turn builds upon OpenFlow and the like. And CORD, which is the central office re-architected as the data center, is a complete data center solution for the edge of operator networks. And if you haven't heard about CORD, I encourage you to Google it. You see a recent quote where nearly 40% of all customers are going to be supported on services powered by CORD within 5 years. A really significant project. I mean, all 4 of these are really moving the needle quite significantly across the industry. So I just wanted to set that context, but importantly, we're going to be talking just on the next few slides about ONOS and OpenFlow. And really P4, the whole P4 tool chain, everything we've been talking about is really, can be considered as the next generation of OpenFlow. How do we address the shortcomings in OpenFlow and really enable the next wave of SDN networking? And that's what we are doing and what we're going to be demoing next week. So, the ONOS running on OpenFlow is shown on the left here. And, you see ONOS running on top of a fixed function data plane and using OpenFlow to do table management, to control the data plane. But these, fixed function data planes, the ASIC defines the data plane. The data planes, or the pipelines tend to be quite complex because they're trying to envision every possible scenario that might come up. And every vendor's implementation is different. And so what we've learned over time, I mean, OpenFlow started off being relatively simple, but over time it had to be extended again and again to support different protocols and different pipelines and different scenarios. And what we've discovered is that the controller needs to be tweaked to accommodate variations in the forwarding pipeline. And what this ultimately leads to, the solution is not as nimble as one would like, and innovation is stifled. It's harder. Yes, you can swap out the data plane, but it's not a trivial plug-and-play process. And so, what we're headed towards here with P4 is really addressing this issue on a number of fronts. And so, on the right here is, kind of a high-level depiction of what the demo looks like. It starts with the P4 program in that upper left, where you have the definition of the pipeline, and that pipeline is then compiled. And then artifacts from that compilation are imported both into the ONOS controller, and ONOS pushes the compiled program down into the data plane. And in so doing, dynamically, changes in the pipeline can be accommodated by the complete solution, including both the data plane and the controller, without having to go in and manually tweak the controller. And so one can now innovate in the data plane. The environment can accommodate those innovations without manual intervention or even without a reboot. So live networks can just be upgraded on the fly. So this depicts how it works with the programmable forwarding plane. But I think there's a really interesting learning we've had just over the last few years, and really Jim from Google was getting into this, in that this has a tremendous benefit even with fixed function pipelines. And that is that instead of pushing the compiled P4 program down into the pipeline, one can use P4 to describe the fixed function pipeline. You almost think of it as pulling P4 out of the fixed function pipeline, using that to define the program in the upper left, and then continuing to use the rest of the tool chain as before to compile it and to import those artifacts into the controller. And in this way, one can get around the the tweaking that's been required in the past using OpenFlow. And so we think there's a tremendous benefit here as well, even when the pipeline itself is not reprogrammable. So next week at the SDN World Congress in The Hague in the Netherlands, we're going to be demoing, kind of pulling all these pieces together. And the 3 players that are on the call today all contributed significant components, and this kind of walks through some of those details. From ONOS, ONOS will be using P4 Runtime to manage a complete spine leaf fabric, a data center fabric. And it's going to support configuration of the data plane by downloading the compiled P4 program through ONOS, and then the manipulation, the read-write management of the fabric using the P4 Runtime running over gRPC. Google has configured the Tor.P4 program, and this is going to be used as the pipeline definition for the demo. And then Barefoot is demoing or providing hardware switches, both the 6 terabit and the 3 terabit versions of their switch, And we're also demoing and running over the BMV2 soft switch. That's an open source soft switch that's available. So looking beyond the demo, we have a couple of things coming. The next immediate steps are, number one, switch configuration via OpenConfig, and also extending the P4 runtime to run on other switch vendors and other ASICs. And then to support new and existing ONOS applications with any P4 program. But in the short term, that is done with manual mapping of ONOS to P4 inside of ONOS. But in the longer term, we want to push that forward and incorporate the ability to understand P4 programs inside ONOS to provide then automatic mapping of ONOS to P4 inside the ONOS controller. We're rethinking the northbound API out of ONOS to enable the full potential of P4. And then thirdly, there are a number of really interesting use cases we think this all enables. And we're pushing the needle forward in a bunch of ways here as well. The first is in-band telemetry. P4 has been recognized as a great tool to be able to get much better visibility into the running characteristics of a network by tagging packets and being able to see the details of every flow in the network. With that ability, to be able to do spine leaf fabric optimization, to be able to spot elephant flows and then to be able to dynamically, move those to run through a different spine to be able to balance traffic on the network and avoid bottlenecks and hotspots. And then thirdly, VNF offloading. There's, we believe, a lot that can be done to take functions that have run in x86 servers and start to push that into Fabric. So then in closing, I want to talk about the vision, sort of the big picture of where this is and where we think it's headed at the ONF. We believe our mission, our charter, is to continue to push the edge on networking, and we think there's a lot that's on our plate right now that we're very, very excited about. So, NFV and VNF came about a few years ago, with a lot of hype and excitement, and really with a vision of taking functions that were running in fixed purpose-built devices and running it on COTS servers, white box servers. But the first wave of that was on these monolithic VNFs, taking a function like a firewall and just porting the whole thing to an x86 server. And what we learned is that this really failed to deliver the hoped for economics and agility that one was thinking of at the beginning. The next wave of this was really around microservices, and this is where Cord is today, about taking functions and breaking it into very small components, running it in containers, and being able to disaggregate it and then rebuild services dynamically, and in this way really achieve cloud agility. And with this, we've really now achieved the economic crossover, and we're starting to see great benefit in the way networks can be built and designed. With P4, we think there's some really amazing potential for things that we can do. So, what we're envisioning and what we're driving towards is taking services and functions and decomposing it into the micro components, but having some of these components running on x86 and some of these components running in Fabric as flow services, running in a P4-enabled Fabric. And anything we can run in Fabric will run at 100x performance improvement over an x86 at 2 orders of magnitude. And so the cost savings, the power savings, the footprint savings are just astronomical and very exciting. We've actually already been delivering some of this with ONOS and Cord today, that some of the services we actually use OpenFlow and push into the Fabric, but we think we can do much, much more with P4, so we think this is a really exciting path forward with tremendous, tremendous potential. So in closing, I just want to invite everybody to learn more and to join the community. This is open source work. We do everything we can in the open, and there are numerous ways to plug in. And I want to highlight 2 here today, specific to the P4 work and the P4 runtime. Within the ONOS project, we have the P4 Brigade and the pointer here. And also within p4.org, the API working group is where the P4 runtime work is being defined, and there's a URL here where you can learn more. So with that, Simon, I'm going to pass it back to you.
Okay, thanks very much, Timon. And Just before we go on to the Q&A and our last poll question and the Q&A, I'd just like to quickly summarize what we've seen. So we've seen web scale and telecom operators are pushing for greater control of large networks. We've also seen that switch devices are becoming more programmable, but OpenFlow only provides limited control of the switching hardware. And as several people have said, OpenFlow is, however, an open interface with significant industry support. P4 is used to specify the packet forwarding behavior in some smart NICs and switch devices, and we can take advantage of this by using P4 Runtime to support a fully flexible and open interface between network controllers and switch data planes. So with all that in mind, this brings us to our last poll question, and what we'd like to ask is, how interested are you in being involved in the P4 Runtime project? Is it something you're already involved in? Is it something you'd certainly want to be involved in? Is it likely that you'd like to be involved? Or would you just like to know more about P4 Runtime? So once again, if you can make your votes as to which is most appropriate to your particular situation. And we have had quite a few questions come in already, but please keep those coming in and we'll try to get to as many of those as we can. So we've got some results coming on the poll, so we should be able to push that out now. Just coming up on the screen. And that's roughly a third, and about 10% already involved. I wonder, Nick, do you find that encouraging?
Yeah, I think that we can expect more and more people to start looking at this as the underlying problem is real. I think that there's a lot of frustration in the industry with closed and inflexible APIs, and we've really been held back for the lack of them, for lack of more open and extensible and interfaces. So I think there's a lot of reason to think that more people will get involved over time.
Okay, great. Right, well, let's go on to the questions that we've had come in. And I want to go to this one first, and perhaps we can go to Nick on this one. The question is, how is P4 different than OpenFlow? And I don't know if Jim wants to come in after that.
Yeah, sure. You could think of P4 as being much more general than OpenFlow. OpenFlow gives you a specific way to describe a set of headers to match upon, whereas P4 lets you describe any forwarding behavior that you want. There is, in fact, a program called OpenFlow.P4, which just takes the fixed version of OpenFlow and describes it in a P4 program. So P4 is a language that allows you to describe many forwarding behaviors. If you'd like to learn more about that, there's actually a blog post at p4.org that Jen Rexford at Princeton and I wrote, really going through the differences between OpenFlow and P4.
Okay, great. I don't know, Jim, if you wanted to come in on that and give the operator's perspective on that question.
Oh, I think Nick covered it well, thanks.
Okay, that's great. Right, so question for Timon here. When will it be possible for ONOS or ONF team to have native P4 support?
So, of course, in this demo, what we're doing is a form of native P4 support. I mean, it is the first step, but it is true P4, and both, supporting P4 programs and the P4 runtime. And, the timeline might describe a short and longer term. I mean, those short-term goals, we move pretty fast here, and so we're really talking about maybe 3 months away, are the kind of numbers I'm seeing and hearing, to be able to make some significant steps forward. So things are moving rapidly. We think all the pieces needed are now in place. We think this is really exciting, interesting, important work, and so we plan to move this forward quite rapidly.
Okay, great. Anyone want to add anything to that?
Yeah,
okay.
ONOS was this is Nick here. ONOS was designed originally to work with a variety of SAS-band APIs, including OpenFlow, but because P4 runtime is more general, it lets ONOS fairly easily adopt it. But and as Timon said, I think we can expect to see ONOS integrating P4 much more centrally over time.
Okay, that sounds good. Right, so I've just actually pushed the survey onto your screen. So if you'd just like to take a few moments to fill out the survey while we go on to some more questions, And when you fill that in, click the Submit Survey button at the bottom. So this next question, I'll perhaps go to Jim initially. So the question is, does monolithic VNFs imply moving away from Intel DPDK SDK to P4 runtime implementations?
I haven't used Intel's, I think, packet processing libraries, but from my limited understanding, I would assume that P4 might be an extension, might be a new way to program, or the DPDK could be extended to use P4. But we haven't used it, so I probably don't have much insight into that.
Nick, or
I'm happy to take that if you want, Simon, too. And so, the way we are actually using both, in the way, Cord is architected. And I think this question is probably prompted by, some of my discussion about monolithic VNFs and our vision for microservices and fabric services. So, when we decompose virtual functions, the parts that run on the x86 can still really benefit from DPDK and to accelerate their networking capabilities. And so that's still, an integral and important component. But then the elements that run in the fabric itself will be using P4 and running down in the fabric. And then, service composition, service chaining, service graphs will then, tie those all together to craft, something that's actually be delivered to a subscriber or an end user.
Okay, great. So actually, I wanted to stay with you, Nick, for this next question. So the question is, typically technology provides either complete flexibility or line rate performance. So could you explain how with this approach you can deliver both?
Yeah, I think we're all aware of the conventional wisdom that says that packet switches had to be fixed function, otherwise they would be slower, consume more power, etc., and cost more. And frankly, with benefit of hindsight, I think it's easy to say that we were not really stepping back and thinking about this the right way. Over the last few years, we had the opportunity to sit down and say, what is the correct domain-specific processor that we would need for networking in order to process packets? And this is what Barefoot has been doing, but represented somewhat by that PISA architecture. That's sort of a cartoon version of how a device like this might work. Like we've seen special processors for graphics, GPUs, for signal processing, DSPs, and now for machine learning as well. Networking has maybe been a little bit late to the game in coming up with its own type of processor for processing packets. And so what this allows us to do for the first time is to process packets defined by a program, a high-level software program written in P4 that runs at line rate, consuming the same power and takes no more area on the silicon, so it therefore has the same cost structure. So in my mind, this is just something that needed to happen, and quite likely that all future switching chips will be built this way.
Okay, thanks, Nick. So I've got a specific question here for Jim. Besides data center use case, does Google plan or envisage leveraging P4 to further enhance its global SD-WAN on top of the famous B4?
Great question. Yes, actually, our first application of this will be for the B4. It is planned to be for the B4 wide area networking, and that's only due to the nature of where we need our next enhancements and next level of technology. So, yes.
Okay, great. I'll go to Timon first on this question, although the other two may want to come in as well. Can you please clarify how P4 runtime reduces complexity? Does it need different schemas for different hardware pipeline implementations?
Well, so when you have, programmable forwarding planes, no, the same, schema can just be pushed down. And I guess, schema, we're talking about the P4 program, I presume. But maybe this question is about if you have, different forwarding, fixed function forwarding pipelines, and you're trying to model those in P4, in which case there are kind of two ways to answer that. One is that, yes, there would be different P4 programs to model specifically those fixed function pipelines. But Jim from Google did describe the ability to abstract that pipeline with a simplified pipeline that could run on, be uniform and run on different data planes and pipelines. And so in that way of thinking, that's a common quote-unquote schema, P4 program that's running on different hardware platforms. And maybe, Jim, you want to follow that up.
You had that right, Timon. Our plan is to have a simple pipeline defined or schema defined that can be realized on multiple different types of chips. And instead of having a different pipeline for each type of chip, we would actually have a different logical pipeline or schema, as the questioner asks, for different roles. So a top-of-rack switch might have different functionality than an edge router. And then what this abstraction approach allows us to do is deliberately introduce changes. So if we get a new generation of hardware and we want to introduce that switch use into the network, we can have a slightly different schema for that switch, but that's an explicit control decision for which we can implement and support. So in that way, the control is in our hands. The complexity has mostly been pushed to this compiler and the implementation in the switch software to map the pipeline, logical pipeline to the actual physical hardware.
Okay, great. I'm going to go to the next question now. I think, Nick, perhaps you'd like to take this one. So is there any applications traditionally run on an x86 that can run on P4 switches?
Yeah, that's a great question. When we think of making our forwarding planes programmable, we tend to think to start with, oh, how do we do the same old that we've been doing for a long time? And in a way, we've been lulled into thinking this by a networking industry that's been somewhat ossified and stale. We think to start with, how do I move my IPv4, my Ethernet, etc. But as soon as it's programmable, it's quite amazing to see how people's eyes open as they suddenly realize there are many things that they've previously put outside of the network they can now fold into the network. Things like load balancers. Layer 4 load balancers traditionally consume hundreds or thousands of servers inside big web-scale data centers. You can now fold those into the plumbing layer, the networking infrastructure, by simply adding a program, a P4 program to a switch. Things like DNS caches, things for doing DDoS mitigation, even things that accelerate storage. So there are many things that you can place into the infrastructure that you couldn't before, simply because it's programmed. And the really big one that has taken off more recently is measurement. And that's because people who own big networks have been, they're the ones that know what they need to be able to measure and see. And so once they're armed with the ability to change the forwarding behavior so they can see the details of packets that have previously been invisible to them, then they do that. And the way in which they do it is specific to particular context, to particular networks. And so the flexibility really is really helpful to them.
Okay, great. Does anyone else want to come in on that one? Okay, so we'll go to this other question, and I'll perhaps go to Jim initially, but Timon, you may want to come in as well. So here you talked a lot about controller-based networking. How do you envisage a hybrid approach where network still runs common control planes such as BGP and controller pushes advanced functionality using P4 runtime?
That's a very interesting question. The way we would do it, I'm not sure this is the way everybody would do it, but we would have the BGP running on top of some software which used P4 runtime to push the forwarding state generated by BGP into the hardware. That way everything would be accessing the hardware through P4 runtime, and whether it be networking protocols, security applications, or other types of forwarding applications would all be using P4 together.
Okay, great. Timon, did you want to add anything to that?
Yeah, I do actually. So, the way we think of it actually is, we do this today, but maybe not quite how the questioner was thinking, right? So, if you look at an ONOS implementation or a core data center, we run the BGP protocol, in software on an x86 to, exchange with the peer routers. But then we use that intelligence using OpenFlow today to push rules throughout the fabric to be able to do all the routing so that no packets then have to hit any software processor. And it essentially makes the entire data center fabric run like one massive router, and every one of the white box switches is almost like a blade in a chassis-based switch. You might think of it that way. So, we are blending the traditional protocols, the control protocols, with the SDN techniques, but we do it that way because then that island of a core data center has to be compatible with the existing network, and the existing network uses BGP and other routing protocols. So I think a little bit different than maybe the question was intended, but in the real world, it's always a blend, frankly, to be able to really introduce new technologies.
Okay, great. Well, I think we can just sneak one last question in. Maybe, Nick, you'd like to answer this. So I'd like to learn about P4. What's the best place to start?
Great, yes. There is a website, p4.org, p4.org. If you go there, you'll see all things P4. You'll learn about the other companies that are involved, the P4 language specification, which is open source itself and is an Apache licensed language, so anybody can use it for any purpose that they want. There are also a number of tutorials that take place from time to time. We have a workshop every year in May or June, and then there are Developers Day. There's one coming up in November at Stanford University, and come along if you can.
Great. Okay, well, I'm afraid we've run out of time. Thank you for attending today's presentation, P4 Runtime, putting the control plane in charge of the forwarding plane, brought to you by Light Reading and Barefoot Networks. And on behalf of our speakers today, Nick McEwen from Barefoot Networks, Jim Wanderer from Google, Timon Sloan from ONF, and myself, Simon Stanley, thanks for your time and have a great day.